Dear all, welcome to the presentation on vapor power cycles. The subject is thermofluid science. In the earlier lectures, we understood about thermal power plants and its evolution. Especially, the focus has been given on energy evolution as well as this exergy evolution. Now, this lecture is focused to understand the exergy evolution of a thermal power plant through an example of regenerative Rankine cycle. A Deaerator, that is open feedwater, has been selected to demonstrate the Exergy solution of the regenerative Rankine cycle. Coming to this numerical problem on regenerative Rankine cycle to show the Exergy solution. In a typical steam power plant, steam has been generated from the hot gas at 350 degrees centigrade and 3 lakhs normal meter cube per hour. The steam turbine inlet condition is 16 bar and 325 degrees centigrade. The condenser pressure is 0.1 bar. Consider a Rankine cycle with Deaerator, that is a regenerative Rankine cycle, at a mid temperature of condenser and boiler. Take 85% of steam turbine isentropic efficiency and 75% for pump. Evaluate using second law of thermodynamics, that's Exergy. Analyze the irreversibility losses at each and every component. The circulating water inlet temperature in condenser is 25 degrees centigrade with a temperature rise of 8 degrees centigrade. Molecular weight of hot gas is 29 and its specific heat is 1.03 kilojoules per kg Kelvin. The hot gas exit temperature is 200 degrees centigrade. In the given problem, the source and sink conditions have been given. Hot gas at 350 degrees centigrade and flow rate 3 lakhs normal meter cube per hour. And similarly, the boiler conditions at 16 bar and 325 degrees centigrade has been furnished. The condenser condition is 0.1 bar with circulating water temperature, supply temperature 25 degrees centigrade with rise of temperature 8 degrees centigrade. The solution, before solving the solution, going to the solution, first we have to furnish the details of the plant, that's especially the TS diagram, the schematic as well as the TS diagram. The first figure shows the schematic of this regenerative Rankine cycle. The steam enters the turbine at 1, the steam is taken out for Deaerator at state 2, and steam is expanded completely at stage 3, and 3 to 4 is the condensation, 4 to 5 is the pumping from condenser pressure to Deaerator pressure. Whereas in second pump, the pressure is rise from Deaerator pressure to the boiler pressure. So these all are shown in the TS diagram. 1, 2, 3 shows the expansion, 3, 4 is the condensation, and the pumping 4 to 5 as well as the 6 to 7. 7, 8, 9, 1 is the boiling process, that's 7, 8 is the evaporator section, 7, 8 is the economizer part, 8, 9 is the evaporator, and 9, 1 is the superheater. The red line shows the hot gas and this blue line shows the circulating water. This is also TS diagram but drawn to scale, the temperature scale as well as this entropy scale. The given data is gas inlet temperature Tg1 is equal to 350 degrees centigrade. Gas outlet temperature is also given 3G2. Tg2 is 200 degrees centigrade. Mass of the gas is 3 lakhs normal meter cube per hour, and boiler pressure is P1 16 bar. Turbine inlet temperature is 325 degrees centigrade, and condenser pressure P2 is 0.1 bar. The gas is given in volume. The volume is converted into the mass by means of this Avogadro's number 22.4. The using this equation, that is a volume multiplied by molecular weight divided by 22.4 and 3600. So 3600 is converting the hours into the seconds. Finally, the supply of gas is 107.88 kg per second. The saturation temperature of the boiler at given pressure of 16 bar from steam table is 201.37 degrees centigrade. This is the saturation temperature of the boiler. Similarly, the saturation temperature of the condenser at 0.1 bar from steam table is 45.83. This is the 45.83 degrees centigrade. Now the deaerator temperature is located between the boiler saturation and condenser saturation temperature as per the given constraints. So the deaerator temperature, this is the saturation temperature, is equal to saturation temperature of the condenser. This is the condenser saturation temperature of 0.5 into saturation temperature of boiler minus saturation temperature of the condenser. So that is equal to 123.60 degrees centigrade. Now the saturation pressure of the deaerator at 123.6 degrees centigrade is 2.22 bar. Before going to the Exergy evaluation, first the entire Rankine cycle has to be solved using this energy, that is using first law of thermodynamics. That is, at each and every state, enthalpies has to be solved by mass balance as well as this energy balance equations. For this, either steam tables or Muller chart can be used. So since the earlier lectures is focused on energy solutions, that energy solution is not repeated in this problem, because this problem is mainly focused on the presentation on Exergy solution. So after solving this first law of thermodynamics, the resultant enthalpies are furnished from 1 to 7, where 8 is a saturation liquid point, H1, H2 and so on up to H7. Similarly, the entropy values also furnished here to solve the Exergy of the each and every component. So from the energy balance in heat recovery, the mass of the steam can be determined because the mass of the gas is given. The heat lost by hot fluid in the boiler, that is the mCp delta T of the hot gas, is equal to ms into delta H of the steam. So this energy balance equation is resulting mass of the steam as 6.4919 kg per second. The blood steam is required to raise the temperature of feed water and also to condense the blood steam into the saturated liquid condition. So there are two mass are mixing here, that is a mass steam 2 plus feed water heater at state 5 is equal to the mixer that is at state 6. It's M2 plus M5 is equal to M6. This is the mass balance equation, and the energy balance equation is equal to heat loss by the steam is equal to heat gain by the feed water. Our total heat before mixing is equal to total heat after mixing, that is M2H2 plus M5H5 is equal to M6H6, where M6 is equal to M2 plus M5. This energy balance is giving the M2, that's mass of steam required for feed water heater, that is 0.8269 kg per second, and steam turbine output is equal to some of the two stages. In first stage we can say this is state 1 to state 2, and in second stage this is state 2 to state 3. So M1 H1 minus H2, whereas in stage 2, since some steam is used for feed water heater, M1 minus M2 is the amount of steam expanded in the subsequent process. So the gross output from the steam turbine is 4,596 kilowatts. That's 4.596 megawatts. And the net input to the pump is again there are two pumps here, the pump 1 and pump 2, that's M4 H5 minus H4, and second pump M6 H7 minus H6. So after adding these two pumps, that's 57 kilowatts. The resultant work input to the two pumps is 57 kilowatts. After subtracting this work input the pump to the turbine, the net output is WT minus WP, that is equal to 4539 kilowatts. That's it's 4.539 megawatts. The heat supply, the amount of heat supply in terms of energy is mcp delta T. That's also equal to m into delta H of this enthalpy. You can calculate either from hot fluid as well as this cold fluid. That is equal to 16,669 kilowatts. This is the amount of energy supplied to the plant. This gives the first law of thermodynamics, that is the thermal efficiency of the power plant, Rankine cycle. Regenerative Rankine cycle is output by input. The output is net output from the turbine, and input is heat supplied in the boiler. That's is equal to 27.23%. This is the first law efficiency, as well, also called as energy efficiency. Now, for Exergy evaluation, that's especially the analysis, irreversibility or Exergy loss at each and every component has been determined. This is the equation used to find the irreversibility of the component or the process. The total entropy generation multiplied with T naught is equal to irreversibility. Or this is also can be calculated from the Exergy balance. T naught into delta S of this hot fluid plus the same T naught into delta S of the cold fluid, that the steam, has been determined here. It's coming 13,360 kilowatts of loss. So there is a loss, some considerable loss has been found in heat recovery. And turbine is also determined using the similar equation, that is delta S of the universe, that is delta S of the system 1 and delta S of the system 2. Here the delta S of systems, we consider only turbine because there is no heat loss. We assumed the steam turbine is completely insulated. That's why entropy generation of steam turbine itself is taken to calculate the irreversibility of the steam turbine. This is the first stage entropy, and this second term is the subsequent expansion of the steam, that is entropy generation. T naught into M1 S2 minus S1 plus T naught into M3 S3 minus S2. That's the final entropy minus initial entropy. That's entropy rise. This is showing 681.25 kilowatts of this Exergy loss or irreversibility loss. A deaerator is the component, that is feed water heater. This is actually the Exergy loss is the decay is due to the mixing of the two stream. The final entropy minus initial entropies are considered here. The final entropy is M6 S6, and the initial entropy before mixing is equal to M2 S2 and M5 S5. After multiplying this T naught, it is coming as 151.7 kilowatt. It's compared to other components, the reversibility loss in the year it is small. In the condenser, the amount of circulating water required is determined from the heat balance, that's heat loss by hot fluid is equal to heat gained by the cold fluid. Here hot fluid is condensed steam, and cold fluid is the circulating water, and the circulating water heat is mcp delta T. So the water inlet temperature is 25 degrees centigrade, water outlet temperature is showing as 25 plus 8 as per the given data. So amount of circulating water required is 416.72 kg per second. So from this mass of the circulating water, amount of irreversibility in the condenser can be determined again by the change in entropy in circulating water as well as change in entropy in the condensed steam. It is resulting is 724.67 kilowatts. The pumps, there are two pumps here, the irreversibility and that's from the entropy rise in pump 1 as well as this pump 2 is determined that it's S5 minus S4 here S7 minus X6, that is equal to 48.38 kilowatts. And in addition to the components, there is a loss at the exhaust gas after this heat recovery, as well as this hot water is coming out from the condenser. These two also to be accounted to balance the exergy, total exergy of the plant. So the irreversibility associated in the exhaust is equal to exergy value of the hot gas. Exergy value of the hot gas is equal to Q minus T naught into delta S. So here Q is amount of heat loss to the surroundings, and delta S is determined from Tg2 up to the surrounding temperature, because the reference temperature or dead state for Exergy is T naught as well as P naught. The exact Exergy associated or reversibility loss in the exhaust gas is 4146 kilowatts. Similarly, the exergy loss or exergy associated in the hot water also is determined um, as from the heat loss to the hot water as well as entropy generation from ambient temperature or dead state to water exit temperature. It's 183.23 kilowatts. So the components of steam turbine, condenser, pumps, deaerator and boiler has been determined. In addition to these components, uh, the fluid loss, that's hot exhaust gas as well as hot water from the condenser also accounted. The total irreversibility loss from the plant is the sum of heat recovery, that's a boiler, steam turbine, deaerator, condenser, pumps, that's two pumps, exhaust and hot water. It is 7269.2 kilowatts. And similar to the energy of the hot gas, exergy of the hot gas also can be determined from heat as well as its entropy values. Mg delta T from dead state is a amount of heat, total heat. This is the total heat from the dead state, and the entropy component is Tg log of Cp log of Tg1 by T1. This is in Kelvin. After substituting this data, we got 11,691 kilowatts of this exergy of the hot gas supply. The actually in second law, as per the second law of thermodynamics, the exergy supply and total irreversibility is the output. That is the second law output, exergy output. The exergy output is here 4021 kilowatts, which is approximately matched with the uh, output calculated from the steam turbine using energy formulations. So similar to the energy efficiency, exergy efficiency also defined as exergy output by exergy input. Exergy output is, that is the work output, and exergy input is the exergy associated in the hot gas. After supplying this, substituting this all this data, we got 38.82%. It's above the first law of thermodynamics efficiency. This is the second law efficiency. Second law efficiency or exergy efficiency is 38.82%. This Rankine cycle, that's regenerative Rankine cycle, can be solved using the software, using the properties, steam properties, and hot gas properties. And chart, similarly, chart can be prepared. This bar chart can be prepared to compare the irreversibilities associated in each and every component. Here, irreversibilities are converted into the percentage of exergy of the hot gas supply. So it is showing 11.41% is exergy loss in heat recovery, and in steam turbine it is 5.827%, and Deaerator it is small, it's 1.298%. Condenser is medium, it's 6.199%. Pump is very small compared to all other components, it's less than 1%. In hot gas it is more 35.46 percent. So there is a chance to recover still some more energy as well as this exergy from the hot gas. The power means this is the second, this represents the second law efficiency, that is 38.82%. Similar to the hot gas and hot water also losing some of the exergy, that's 1.5%. It is compared to hot gas, the exergy loss in hot water from the condenser is small. Thank you for your listening.